We'll be discussing linear regression today, right? So linear regression is important because one, it is a linear model, right? Uh, so linear models, I mean, at times are not very useful if you look at the whole thing, but they are easy to understand. So as a starting point, they are good. And once upon a time, I mean, when the world was not complicated, the computing power was not available, then linear models were one of the mainstay, right? So having no model versus having some model, that was the kind of idea, right? So they have served for a very long time. I mean, if you look at the area of econometrics, then they have served for a long time. Nowadays, better models are available, of course, because machine learning AI now picking up, and we can almost model anything. So the value of the linear models definitely has gone a bit down, but at times they are useful. I mean, and our learning has to start from there. Okay. So the other idea is so where does it start? So it starts from we discussed during descriptive analysis, we discussed correlation. So how do we measure the association between two variables? So we'll say it is correlation coefficient, right? So correlation coefficient is small r, right? So what is the correlation between them? Let us take this example, like there is a researcher or he believes that there is a linear relationship. The word linear relationship is important. If there is a belief of linear relationship, then only linear model or linear regression should be used, otherwise we cannot use it. So there is a researcher who believes that there is a linear relationship between BMI of pregnant mother and birth weight of the newborn, right? Okay, so a researcher believes that there is a linear relationship between BMI of pregnant mothers and birth weight of the newborn, right? So more is the BMI of the mother, more would be the birth weight of the newborn child, right? So 15 data points are picked up, right? So these are the 15 data points. This is BMI is generally measured is body mass index. So this is kg per meter square kind of unit it has, and birth weight has to be in kg. So these are given. This data is given. So the first thing that we can do is because this is a visual method, is we can just go in for a scatter diagram. So let's say we make a scatter diagram, and once we make a scatter diagram, what we see here is that this is what is there, and so these are the points. This is my scatter area, right? So these points are there, right? That we are seeing now. If so, okay, let's move to the next slide and then discuss. So if I calculate generally, this is how I understand correlations, isn't it? So I say that if the mod of r, that we always take the mod of r, so if it lies between 0 and 0.40, now these are not very, let's say, hard coded figures. There may be some slight variations in this. So if the value of the correlation lies, somebody will say if the value of the correlation lies between 0 and 0.30, then it is weak correlation, right? Mm. So a tentative idea, 0.40 to 0.59 is medium, but everybody agrees that if r, this should be small r, is greater than or equal to zero point 0.6, it is a strong correlation, right? This is definitely correct, right? So correlation value of 60% or zero point 0.6 is definitely strong. Okay, so if I again go back to the previous slide, and then there would be some kind of a correlation that I'll get, right? So this will represent some kind of a correlation, and if this correlation, how do I read, like if it is a weak, medium, or a strong correlation? I can use this and understand what kind of a correlation it could be, right? And this we have done, right? And when we say analysis, it's generally univariate, bivariate, and multivariate. So this was a bivariate analysis where we are taking two variables and we are trying to understand correlation or covariance. Now we are getting into multivariate. So multivariate means that whenever we use two variables or more than two variables, that's known as a multivariate analysis. Okay. Also there is the idea of a correlation. So what happens when there are multiple variables, right? So we'll think about this. So if there are a b two variables, we find out correlation between them. But let's say there are three variables a b c, right? So a b c, what we can do is we can use a excel and we can find out a correlation matrix there, right? But understand this situation, that chances are that A is correlated to B, B is correlated to C. Think about it. So what will happen? Something like this is going to happen. Let's say if I'm going to find correlation between A and B, right? Then because my assumption is that A is, and if I look at the correlation matrix, so this is one point that we'll have to think about right now, that let's say this is my correlation matrix, okay? Add one more here, right? So the correlation matrix is like this, that this is my A here, this is my B here, and this is my C here, right? So and the correlation matrix will look like this: A, then you have this A, you have B, and then you have C here, right? So the diagonals are going to be one. So this is one, and this is going to be one. The diagonals are going to be one, and these may be any values. Let's the BB is going to be one, CC is going to be one. A to B, let's say it's a positive correlation of 0.5. Let's assume this, right? And B and C, A and C is again a positive correlation, a very high correlation, let's say 0.8 for some reason. Okay, and B and C has a negative correlation, which is minus, let's say 0.6. Okay, so this is what the correlations are. Now, if you look at it, if I find the correlation between A and B, always understand, and I represent it by a arrow. Let's say in path analysis, there is one more area in when people work on typically marketing analytics projects, then what happens is they try to find out what are the key driver analysis. What is the key driver analysis? What are the reasons that that a product X is being sold, right, versus product Y, right? Both of them are selling in the market, both of them are competing, and generally they have different reasons for selling, isn't it? So they are known as key drivers. What are the key drivers for selling this product? So they use a technique which is known as path analysis, right? Something like path analysis. Just let me answer Ganguly. I think he has woken up. Hello. Hi, morning, Ganguly. I'm in a session right now. We had a session. Okay. Yeah, yeah, yeah. Okay. No, no, no. No, 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 no. Okay. So, so if I look at this, then there is something known as path analysis. So if you work on marketing applications typically, then path analysis is something which is very important. We may not cover in this, but remember this is known as path analysis. So A to B, right? So if I want to understand this strength of this relationship, I'm trying to say A to B, like what is the kind of strength. Now what can happen is that this strength of A to B may be something like this, right? So C may be influencing your A. So path means what is influencing what. So you show it like a diagram, that's all. So C is influencing A and A is influencing B. So this is here. So if I find the relation between A and B, actually there is some component of C to A also in this, isn't it? Because so C is not directly influencing B, but C is influencing B via A, right? So now what do we have? This correlation coefficient that you have, it captures everything. So there are two kinds of effects, right? Let me quickly like wind up. This may not be topic here, but is an important thing that we discuss here. So we say that these effects can be of two types, right? One, it could be a direct effect, right? So the effects could be one, it could be a direct effect, and the other could be something known as a indirect effect, right, coming via something else. Like let's go back to some examples that we that I discussed in correlation example. We had discussed the correlation of eggs, like eating in Delhi being highly correlated to raining in Chennai. Now there could be some other variable. Now what we are doing is, this is, let's say, raining in Delhi, and this is eggs eating in Chennai. So when we are looking at it, probably directly there may be no correlation, but there could be third thing which is not available to us, and that is related to this also, and that is related to this also, right? That could be the reason that we are seeing this kind of effect, right? So always remember that when direct, the effects can be direct and indirect, right? So when we try to filter out this indirect effect from the correlation, and whatever is then left, the direct thing, whatever is left out of it, this is known as partial correlation. So correlations can be of many types, right? We discussed this, or probably just let me show it to you. This is one important thing that we need to know. Okay, so your correlations can be, let me just open this one. So there is something known as partial correlation. Okay, so the partial correlation, so this you can read very quickly, is a measure of the strength and direction of linear relationship between two continuous variables controlling the effect of one or more continuous variables, right? So if known as covariates or control variables. Yeah, there is one more thing. What I'll do is that the books that I was trying to pass, I just remember why I could not pass them is because some books I've already passed to Ganguly. There are few other books that I've not been able to pass because their size is very big. So generally this Gmail will not allow more than 25 MB, and this book whose name is this Ken Black, it has a size of 69 MB actually. So that is the reason it is not passing. So I'll put it on a Gmail and give a link. So either Ganguly can copy it there, or you all can copy it directly from that Gmail link, right? The drive, I'll put it in the drive, so you can pick it up from there. Okay, so this is known as partial correlation. Now you can see that there is a semi-partial correlation, there is a partial correlation, there are many kinds of correlations. Okay, but here, like, we'll also keep in mind that there is something known as a partial correlation. Okay, so partial correlation is about what? Finding out the pure relationship between the two variables and taking care that it's not impacted by the other variables. You can call them covariates, right? So other variables covariates. Anything which impacts the value of a variable is known as a covariate, right? So that is the terminology that we use. So we need to be familiar with the terminology. So covariate. Okay. Now if we look at the, now coming back to this scatter diagram, so if you look at this scatter diagram, then what you see here is that there is a linear, you can summarize this relationship by a linear line, right? Isn't it? We can draw something like this, isn't it? We can draw a line like this. Okay, now we'll spend some time on this idea of drawing a line. Okay, because this is a linear relationship, whenever you have a linear relationship, if you have two variables, then the outcome, if you try to model two relationships, let's say this is y variable, this I'm calling as a dependent variable, and this x I'm calling as an independent variable. What is a dependent variable? Dependent variable is a variable which is explained by the independent variable, right? So if I assume that, then x can also be called as the predictor variable because it is predicting y, right? In that sense, it is predicting y. So there are different names which are given to, in linear regression we call them dependent, independent, in some other we call them some other thing, right? But just understand the idea is that this y is a dependent variable. That means what? That it depends for its explanation on this variable which is known as x, right? That is correct. This y is dependent on x. So for explanation, y will depend on x, right? So that we have to keep in mind. Now, so this is my y here. This variable is y, which is the birth weight, and it depends on its explanation on the BMI, which is I'm designating as x. This is a linear model. Linear model means if it is a two variable thing, two dimension kind of a thing, you can fit a line. But if it becomes three variables, right? So the dependent variable would be one only, always in a regression. We'll come to this, but let's say this is my dependent variable is one, but I have now two independent variables, x1 and x2, right? So this is my independent variable x1 and this is my independent variable x2, right? So these are the two independent variables that I have. Now, so what will happen? What kind of a shape, geometrical shape will I get if I want to have a linear relationship in three variables? I'll always get this plane, right? So plane is a linear model in three dimension, isn't it? Why? Because we have this kind of equation for a plane very simply, right? Y is equal to a naught, which is like y equal to a naught plus a1 x1, right? A1 x1, or you can call it m1 x1 if you want, right? If you want to call it in the slope kind of a designation, and a2 x2, right? This is the equation. And why am I calling it linear? Because the power of everything that we are using, now this is something very, very important. The power of all the variables that I am using is exactly 1. None of the power is less than 1, neither it is more than 1. It's not 1.1 anywhere, neither it is zero point 0.9, nor is it -1. -1 is also an inverse thing. And this is the equation of a line, right? Equation of a line is y equal to mx plus c. Generally this is how we know it, right? So mx is m is your slope, mx, sorry, this x is poorly built, and this is c here, right? So what is your m is the slope of the line, we know this, right? Tangent of the slope. So if this is your line, this angle happens to be theta. If this angle is theta, then m would be equal to tangent of theta, right? We know this, right? We have all read this. So m equal to tan theta. Sorry, so this is tan theta out here. So you can see, so this is the line, and an extension of this is this. So what happens if I have a hyperplane? So I have a line in 2 dimension. If it is 3 dimension, it will become a plane. Think of this plane like a very, very thin sheet of glass, ultra thin sheet of glass, which even falls down on our head, then nothing happens to it. It doesn't hurt us, right? It's very simple. It doesn't hurt us. And what happens if we have more than 3 dimensions? We cannot visualize 3 dimensions on our computer. This is a screen, right? But it, from a line to a plane, it will turn into a hyperplane, right? So hyperplane is a plane with more than 3 dimensions, right? But the same thing will continue, the same equation, a naught plus a1 x1 plus a2 x2 plus a3 x3, so and so forth, and there can be n dependent variables, a and xn, right? So this will continue, we know this. And what is a1? A1 is nothing but it is the slope of keeping x2 constant. If I want to find out the slope of x1 versus y, so this would be that slope. And what would be a2? A2 similarly would be the words that I'm saying, mark those words, keeping this thing constant, the slopes I mean along the line x1 constant, you will get the slope of x2 versus y, that is a2, right? So this itself says keeping one constant and finding out the slope with the other. That's why these can also be known as partial correlations, or you can say correlation is also depends on the slope, isn't it? Correlation also depends on the slope right here. Okay, but these are partial correlations. Correlations are cos theta. Generally, if you want to find the correlation between two variables, it would be generally equal to cos theta. Okay, but here we have tangent theta. Why we have tangent theta? Because these are partial correlations, right? And you know that your tan theta is equal to sine theta upon cos theta, isn't it? So there you can see something there, right? So partial correlations, we have to do little more kind of a calculation out there. So then they are not exactly correlations at time, right? So some confusion happens there. Okay. So now coming back to the line. So the only thing that you need to remember is, if you have digressed a bit, is that this line, we need, if I need to fix a line, then the equation of a line is y equal to mx plus c, right? Mx plus c. This is the equation of a line, right? This is point number 1. The second point is, I'll use different notations when I'm fitting a regression line. I'm just changing my notations, that's all. So I generally write it like this. I'll write beta naught. Beta naught is for slope, right? So this is your beta naught plus beta 1 x1, right? So I'll say these are beta coefficients. Okay, some people call it b coefficient, some people call it beta coefficient, right? That is there. Okay, so beta naught and b1 x1, this is there. Now if I want to fix a line, if I want to draw a line, I generally need 2 points. So if I have 2 points, I can only draw one line through them. There is no chance I cannot draw any other line out of this, but this is just one line. That's all. No other possibility. So as soon as I get 2 points, my line is fixed. I don't have any scope. But let's say if I have 1 point, how many lines can I draw through this? Probably billions of lines, isn't it? There's so many possibility. I can keep on drawing as many lines as possible, right? So if I have just 1 point, then I can draw as many lines as I want through this. Now look at this situation. Let's say these are 15 points, right? So if I want to draw a line, then I need to select 2 points to draw a line. So how many 2 point combination can I draw? 15C2, which is a big number, isn't it? 15 into 14, and that comes to around 105 to be precise, right? So this will come to 105. 15C2 would be 105, right? So and good, this is only 15 points. In generally in a real situation, we can have millions of points. So how many lines you can think of it, right? So some 1 million C2 will mean what? It would be a very, very big number, isn't it? So the number of lines that is possible is 105. Now my question is, which line should I select and why, right? So there has to be some principle guiding which line to be selected and which line should not be selected, isn't it? So when I have this kind of a situation, what I'll do is I'll have to follow some principle, right? So I'm introducing to you the idea of errors, right? So I'll select a line which minimizes my errors. When I say errors, then these are not human errors per se, right? Anything which my model is not able to account for is a model, is an error. So what is an error? Example, let's say this is the line that I choose, right? Now what is happening? The line is not passing. You can look at this line. This line is not passing through any of the points. So it's missing almost all the points. Let me draw it neatly. So we have seen this. Let's say this line, this is not passing through any of the points, right? It's missing all the points. So what is happening? This is missing this point. If I draw perpendicular from here, right? This is the perpendicular here, and this is the perpendicular here. So if you look at these perpendiculars, so this distance, it is this distance is, this is the distance by which this is missing. This is the distance by which is missing this point. Now let's say I designate all these distances as E1, E2, right? Which anything which is above this line, that is on the left hand side, is positive, and anything which is at the bottom is negative. So then what do I have? I'll have 15 errors, right? E1, E2, so on and so forth, isn't it? How many errors will I have? I'll have, because these are 15 points and the line is not passing through any of the points, so I'll have what? 15 errors here, 15 error points, right? Some of them would be positive, some of them would be negative. If I sum them up, then what will happen? Positive and negative will cancel, and it will give me a feeling as if my errors are low, whereas the truth is that it is missing every point here. You can see it here, right? So what I do is, remember I told you the two principles of error. So we'll follow both the principles of error, and we'll, instead of finding out the sum of errors, we'll find out something known as the square of the errors. So sigma e square we'll find out, and this I will vary. How many errors points are there? In this case it is 15, but let's generalize it. Because if this applies to 15, if it applies to 1, it is applies to 15, it should apply to n also, right? Principle of induction. So I equal to n. This is I equal to n to e square. So this is my sum of errors that I'll find out, right? I'm following the two principles of error. One, an error is an error, so I'm neutralizing the sign with e square. And the second principle is that a larger error should be penalized more and a smaller error should be penalized less, right? So I'm following the two principles of errors. That's what I'm doing. Okay. So this is what I'm doing now. Of course, what is a good model? Whichever, a good model is a model which gives me the least error, right? So this principle is known as OLS, right? Ordinary least squares. And then what will I do? I'll just go here and put it like a OR function and say minimize this, right? So now looking at this like a machine learning algorithm, what do we have? The first part says that I have to fit a line, I have to select a line, and when I select a line, I have to select the constant value, or some people call it the bias also, and I have to select the slope, right? Which so beta naught and beta 1 have to be calculated. The second part is always the optimization thing. So this is my optimization function, a very simple optimization function, right? So this is what I'll have to do. I'll have to minimize this, and the third part, as I said, is that there is some statistical evaluation that I'll have to do about my result, right? There are three portions always. Now, this thing, this evaluating this is not a very difficult thing. So, let's say you do not know any operation research OR thing. So then, what will you do here? You'll try to what are the options? We can slide the line, right? So we can have many positions of the line. Let me try this position. We can flip also. We can slide this, we can rotate this. So I can, instead of doing the line like this, can I change the slope a little bit like this, or I can do both, right? So how many combinations are possible? If you look at it, probably I'll have to do millions of operations to get the right line, right? But frankly, this doesn't happen this way. The OLS equations are very, very clear. So that means the equation of beta naught is very, very clear. It's available. So, and generally the algorithm that you use, they will not use a OLS. They'll use something known as maximum likelihood. We'll come to that, like what is a maximum likelihood. So they use a maximum likelihood estimation. We call it a MLE, right? MLE estimation is based on probability estimation, right? This is not minimizing the errors like this. What it does is, it also, this is all because this is optimization technique, so it has to minimize or maximize something, isn't it? All your operation research techniques will either minimize something or they'll maximize something, right? So your MLE also optimizes something, which is generally the probability. So it tries to maximize the probability. It is not a minimization thing, it's a maximization. So it maximizes the probability, and they converge, right? They give the same solution. The OLS and MLE will give the same solution, but this converges very fast. It's a very, very fast algorithm. So that's why you use it. And because of this MLE, we have very clear equations available. So what should be beta naught? There is an equation available how to calculate it, right? So that we can calculate. Once beta naught is available, then beta 1 can be calculated. So how to calculate beta 1, that is also available. So these are actually equations which are available straight away. They converge into these equations and you get a solution here, right? We are not getting into equations because the first time when you run it, it may not be a very good idea. Okay, so what we have discussed is that this is a linear model. So we are into linear regression. We call it simple linear regression, right? So we are discussing something else, simple regression. Wait, just give me a minute. Why is he calling? Hello. नहीं नहीं, I went inside that वो जो your dashboard वहां से open किया है. हाँ. The meeting ID 851757445. 445. Yeah. Okay. So what is happening here is that we um, so this, like, when we I'm audible, right? I'm getting a message that you're not audible. I mean, audio quality. I'm audible, Ajay?
Yes, yes.
Okay. So So this entire thing that we discussed, when you have just one dependent variable, now coming to linear regression, we are discussing linear regression. So if you have one dependent variable, that is right, and we have one independent variable, right? One independent variable, that is x, right? So this kind of a situation is known as simple linear regression, right? I'm writing it in short, simple linear regression. This is what we call it, right? So this is simple linear regression when you have one dependent variable and one independent variable. This is known as simple linear regression. And when you have one independent variable and a bunch of independent variables, example x1, x2, x3, when we have it like this, then this is known as multilinear regression, right? This is always known as multilinear regression, right? This is multilinear regression. Okay, so simple linear regression is too simple, generally not used. The reality is always multilinear regression. Why we are discussing simple linear regression is so that so that we learn what linear regression is. Other thing is, when we are using linear regression, then we can only have one dependent variable. This is a condition, and this dependent variable should be a ratio data always. Always remember this. This has to be a ratio data. It cannot be anything else, right? It has to be a ratio data. Okay, this has to be a ratio data only. And are there any conditions on the independent variables? That means x1 to xn, let's say we are using xn. Is there a condition on any of these variables? No, generally no, right? They can be anything, right? They can be like ratio data, they can be categorical data, anything. But a regression works best. This is one of the condition. A regression works best when the variables are normally distributed, right? This is one of the conditions. If the regression has to work properly, if it has to give you optimum results, then the variable should be normally distributed. That's absolutely a must. Okay, what is the output? The output, it has to be a linear equation. So the output of a linear multilinear regression is what it is. It has to be like this: beta naught plus beta 1, right? Beta 1 plus beta 2 x2. So this was beta 1 x1, then we have beta 2 x2, we have beta 2 x2, and then so on so forth. We'll go on till what time? We'll go on here and say beta n xn, right? So it has to be what? It has to be beta n xn. Right, so this has to be the output of a linear equation. Now the important thing is, once we get this output, so what do we get out of here? We are getting this beta 1, beta 2, beta 3. So at the second step, we need to understand what does this beta 1 mean. I mean, from application point of view, what will beta 1 mean, what will beta 2? So this is a mathematical exercise, good. But from an application perspective, what will beta 1 mean? What will beta 2 mean? What will beta n mean? This is what we need to understand. And the second thing is, how do we understand? How do we evaluate? Now, this is the model. All because we are into modeling now. So always remember there would be a model. Now, in models, some of these models are easy to write, example like this, but we'll discuss some other algorithms which are complicated. Let's say a support vector machine, something known as a SVM. So if I write a SVM, then the equations are not so explicit. I mean, I cannot write a equation, I cannot write a model which you can see and understand. So the models there are very complicated. We cannot write them the way like I've written it very simply here, or we can write it for some other models. So the writing of the model is not possible. Okay, but how do we understand? But one thing is very important in modeling is, how do we understand that the model that we are proposing, and generally if we are into business, we'll propose it for some kind of a business solution. So the model that we are proposing is correct, or the data that was given and the model that we are proposing. So we have summarized the data into a model. So how do we know that this is a true copy? Isn't it? So the data we have copied or we have converted into a model. So how do we understand that this is the true copy? It's not that something has changed, isn't it? So to ensure that, in modeling, it is very important to understand the goodness of fit, right? We assess something known as goodness of fit. What is goodness of fit? The model and the data, how well they go each other, how well the model explains the data that was at hand, isn't it? That the data is a too much of a spread, complicated kind of a thing. From that we summarize it in a model. Now that model I can write as a mathematical equation sometimes. At times it is so complicated I cannot write, right? Both things can happen, but we always have to understand how well is the model that we are proposing fitting the underlying data. So goodness of fit measure, so we have to look at some goodness of fit measure. So what we'll do is, there are two things that we'll do, and then we can go and actually execute it on R. The first thing that we'll do is we'll try to understand what these betas are. This is one. We need to understand what this beta thing is, and the other thing that we need to do is we need to understand the goodness of it, right? These are the two things that we'll do. Okay, so let's go ahead in the presentation and see if I'm not missing on anything. Okay, two things definitely that we'll cover. So this we have covered everything. Okay, simple linear regression. So I've told you this business. Least square regression line I've told you. Okay, so this looks something like this. If it is a two dimension thing, you can see these are the errors. If it is a three dimension thing, you can look at it this way, right? So this is a three-dimensional response plane. Okay, so multiple regression means you have at least one dependent variable and two independent variables. So this is like how I write the line, right? So beta naught on this applications. Once you have the model, you can always predict that is there. Okay, now let's come to the goodness of fit kind of a thing. So I'll write the equation here again. So this would be my equation that I'm always referring. This is why my dependent variable, only one independent variable, again to revise, is equal to my beta naught, which is plus beta 1 x1, right? Beta 1 x1, so on so forth till what? I'm taking it here till beta n xn, beta n and xn. So the first thing is we'll try and understand what these betas are, right? What this beta is. That's very important. So what does the beta actually indicate? That we have to understand. Okay. Okay. So we'll discuss that. Okay. So what does the beta indicate? That we'll have to understand here. The first thing is, what is beta 1? What is this beta 1? So we'll take two cases, right? Let's take this case. X1 is a ratio data, right? This one you need to focus and understand. X1 is a ratio data. The first case that I'm taking is that X1 is your ratio data. Okay. The second, X1 is ratio data. Let's do that. So what does beta 1 mean? Beta 1 means that if X changes by 1 unit, let's say X changes by 1 unit, then beta 1 is the amount that Y will change, right? So the change in Y would be equal to, and will be equal to beta 1, and everything else is kept constant, right? So if I keep x2 to xn constant, beta naught x2 to xn constant, right? No change in them. And if I change x1 by 1 unit, when I say change, it means I can increase also, I can decrease also. So if I increase x1 by 1 unit, then y will change by beta 1, right? If this sign is positive, then if the sign of beta 1 is positive, then what will happen? If x1 increases, then y will also increase. If x1 decreases, then y will decrease, right? That is going to happen. If the sign is negative, then the reverse will happen. If x1 decreases, y will increase, and if x1 increases, then y is going to decrease, right? The opposite thing is going to happen. And this will happen when x1 is a ratio data. Now let's assume that we are picking up the next variable, which is xn, and xn is a categorical variable. When you have categorical variable and when you run regression, this is known as dummy regression, running dummy regression. So your xn is categorical data. your categorical data, right? So categorical data means the first thing that's assume is that it has only two categories. Like let's start with a simple situation where xn has just two categories, right? And one category is denoted by, let's say, mm, A, and the other category is denoted by B, or if you look at it in R, then R will code this one as one. This will be coded as one here, and in R this would be coded as two, right? So in R this may be coded as one and two, or you can call it yes and no, right? Whatever you want to call it, or probably there these are binary categories, so yes and no kind of a situation. So there is some data where it is about yes and no. Example, gender, male, female. So is it a male? Let's say that's their variable. Then yes, no, yes, no, yes, no. Okay, so this is yes, no kind of a thing. Categorical data. So in case xn is categorical, then what does y mean, right? So this xn, if you look at this xn, then what you'll suddenly see is that you'll see the beta this way. Beta yes, something like this you'll get instead of a beta n, you'll get a beta yes, right? So then the question is what happened to the no, right? So how it works is that one of the categories, this no, becomes the base, right? And what does beta yes mean? That if I prefer, if I'm not in the no category, if my value is not no, instead if my value in the row is yes, then the beta is going to rise by beta n, right? It's going, the value of y is going to rise by beta n. So it's a comparison of categories. Also, let's say if there are three categories, then what happens, right? If there are three categories, so two categories we saw, then we have three categories. Okay, so let's say these three categories are medium, low, and high, right? So what will happen is you will get two betas. So this beta with this variable, you will get two betas. So what will be reported here is, because m comes first in, or h comes first in the dictionary, so this will vanish, and what you will get is beta m and beta l. This is what you are going to get. Beta m in beta l is what you are going to get. Okay, so the h has vanished. Now how do we understand this? So that means the number of betas are increased, and similarly if I have n categories, then how many betas corresponding to this one variable? You will have n minus 1 betas. So if you have more categorical data, then what will happen is the number of betas will get inflated by n minus 1, right? So if you have four category variable, then three betas would be reported. One should have been reported, but threes are reported. So your number of betas increase by how much? N minus 2. The more categorical variables you will use, the more betas will come, right? Now there is the implication of this. We'll discuss this, right? In goodness of it, we'll discuss all this. But just understand this, that if you have categorical data, then your betas would be, ideally you should have a constant, and you should have betas equal to the number of independent variables that you have. If you have n independent variables, then you should have n betas corresponding to that, and plus a slope, the plus a constant or a bias beta naught, right? So that means generally if you have n independent variables, all ratio, then you will have n plus 1 betas to calculate. Now think about this data, think about it in terms of data and parameters. These are parameters, right? Whatever defines my model. So if I write my model, these are my parameters, right? So one way of looking at modeling is that it is about estimating parameters, isn't it? So think about this situation. If I have less data and if I have to evaluate more parameters, then errors are bound to happen, right? If I keep my data constant, right? When I say data constant, that means the number of rows, if I keep constant, and if I keep on increasing the number of betas to be evaluated, then what will happen? I'll not have enough degrees of freedom. I'll not have enough data to calculate every parameter, and there are chances that they may be wrong, right? So categorical data at times, that's why, is a risky proposition, because what it does is it will increase the number of parameters that are to be evaluated. And hence, whenever we are doing a categorical modeling, categorical data modeling, then generally we require a larger data as compared to when we are modeling something like a ratio data, right? It always happens for categorical data. One, it becomes complicated because more parameters are to be evaluated, and their understanding is also you can see not that straightforward. How am I saying that? Here two betas would be reported, beta m and beta l. So how do I understand them? If the value would have been high compared to that, if it is beta m, then this is the increase in y or the decrease in y, right? This is how we do it. A little bit difficult, but you'll get used to it once you do it 2-3 times. Okay, so this is one complication. The second is understanding it is complicated. The number of parameters increase, so it puts a pressure on estimation, and when you compute more number of parameters, the chances of one or two parameters going wrong also increases. It becomes high, right? That has to be kept in mind. Okay, so it's not like we can calculate as many parameters as we want. There is a limitation in which they can be correctly calculated, isn't it? So the chances of this parameter going wrong are high, right? So that means it becomes all the more important that we understand how good my model is. This is one part. What is the fit between my model and the data? This is part one. The second part is how efficiently have these parameters been calculated. Are these parameters wrongly calculated, correctly calculated? That we need to understand, right? So that's what we'll do in the second half, in the second part now. So when we are looking at regression, so when we run a regression equation on R, we'll get some output, right? Now this output, you can say I can divide, or I can assume to be like divided into three blocks. I may call them three blocks. Okay, so I look at three blocks to understand the output of a R. Okay, so let's look at that. uh, so the first block is known as the R square block. You can call it the R square block. What do we look for? We look for something known as the R square value. Okay. Right now we are not getting into the calculations of it, right? We'll just understand in the first cut. We always understand how to use this, right? Then we'll later on we can understand how R square is calculated and all this, right? This is also known as coefficient of determination. Some people call it so R square. And R square is understood in a similar way, the way we understand correlation. So R square greater than zero point 0.6 is always a good fit. In anything which is less than zero point 0.6 to zero point 0.4 is a medium kind of a fit. So similar rules like that we have in correlation. So this is known as R square, coefficient of determination. Okay. The question is, as the word sound R square, it's is a square of something. So can R square be negative? So just keep this in mind. R square can be negative, but you'll encounter a negative R square only when you run at least probably 10,000 regression equations. Then only you can get a R square negative. R square negative means that this particular problem is not fit to be dealt like a linear regression. So the solution is just drop it. You can't do much about it, right? If it is a negative kind of R square that you are getting, either drop some variables, retry it, or whatever you do. So, but that is not a linear regression problem. This is what it means, right? And R square can be negative. You can read about it at times, you find. So but if somebody says because the name is R square, so the case may not be that you start saying no, there is no chance it cannot be negative. It can be negative. Okay, there is absolute chance that it can be negative. Okay, so how do we understand? We want the R square. If it is a good regression fit, the R square should be zero point 0.6 or more, that we want. Okay, then R square is a very dangerous thing, right? Let me give an example how it is a dangerous thing. So what happens is, let's say, yeah, last time we had discussed the Boston housing data set, right? So in the Boston housing data set, our dependent variable is the median values of the houses, right? So here we have the median values of the houses as our dependent variable, right? This is our dependent. And what is the dependent? The median values of my houses, right? So that is MEDV. So this MEDV is my dependent variable, and I have 13 predictors here, right? So the MEDV can be called as dependent variable. You can also call it the response variable also, right? So response, independent, many names of the same thing. So there are 13 predictor variables or independent variables, right? Now, if I look at these 13 variables, they were like, just to remind you, the variables were related to either the nearness to the center of the city, nearness to a river, which is the Charles River there, then the people teacher ratio, the pollution, crime rate, all that makes sense, isn't it? I mean, at, at least when we think about it, it makes sense. Yes, that okay, the value of a house in a locality will depend on all these things, right? If it's a polluted area, nobody will like to live, and the value of the houses would be lower, right? Now, for example, somebody adds, I add a variable which probably may sound logical, but I think it is illogical, that I count the number of dogs in the area, right? And if there are too many stray dogs who are roaming around there, then probably it should not be a hygienic area. Let's say that's what my this thing is. So I add one more variable, the 14th variable I add from my side, and I say this is the number of dogs I see on the street. Average number of dogs I see on the street. Now, logically, this may have, I don't know, this may have a bearing on this, but it's a illogical kind of variable, isn't it? But surprisingly, what will happen is, let's say in the first case, you had run a model with this combination, right? And you get this value of r square as r1 square, right? In the second scenario, you again, you add this value of the number of dogs roaming there, and you get r2 square, right? You get this as r2 square. Okay, it denoted like this, like r square. And in the third, you go and add, let's say, the age of cats that you found there. So somehow you are able to understand the age of the cats, and you introduce the 15th variable, that is the average median age of cats that you found roaming in the street or in the houses. Somehow you find that, and let's say that comes to be r3 square. Okay, now you'll be surprised to know that this r1 square is going to be the least. So that means r1 square will either be less than or equal to, there is a chance it doesn't increase, less than or equal to r2 square. This is 1. And also this is less than or equal to r3 square, right? So r square only goes up if you add a variable, and if you and the reverse is also true. If you remove a variable, it is going to come down. So that means r square is oblivious to the fact that this is a useful variable we are adding or removing. It definitely is not sensitized, is not sensible towards that kind of a thing, right? Regression, ultimately, why do I do regression? I need to understand whether these variables make sense or not, right? That is also one of the purpose. So r square, from an information theory perspective, it is not able to sense whether the variable brings some value, should it be there or should it not be there. That it cannot do. It's a, if you add variables, it will go up, and if you remove variables, it will come down. And this can be very, very risky at times, right? So no doubt we want r square to be as high as possible, that we want, but it's a risky proposition. So that means we need something else. So that is why we have introduced something known as adjusted r square. So adjusted r square is nothing but r square only. But what do? We follow the principle of parsimony that is given by, as I said, Henry Occam's razor's principle of parsimony. What it says is that if if I have to, like, let's say there is a researcher who says that, okay, I can tell you the median value of the houses and I need just 5 variables and I can tell you exactly what the median value of the houses would be. This is one proposition. The second researcher comes and he says, I need exactly 10 variables to tell you what is the median value of the houses. Now, the first researcher is frugal, isn't it? He's following the principle of parsimony. He's only asking that information which is useful. So the first and second researcher are giving me the same level of or the same quality of a model, but one is using 5 variables and the other is using 10 variables. That means the second one is not parsimonious when it comes to the use of information. So this adjusted R square is nothing but R square with a penalty, right? So if you look in the formula, it would be something like this. There would be R square there, and then there is a minus term which depends on log of not log but the number of variables, some combinations, a very simple function of the number of variables that we are using, right? So if you use more variables and if you don't add any value, right, then what is going to happen? This R square will get penalized. So adjusted R square is nothing but penalized R square. And what is the penalty? Penalty is nothing but the number of variables that you are using. If you keep on increasing your variables, then what will happen? The value of R, and there is no extra information that is coming. So your adjusted R square definitely will keep on decreasing and your R square will keep on increasing. That is what it is going to do, right? So it calculates the amount of information that is coming per variable kind of a thing, right? If that doesn't sum up here, it's a very small change that it makes and you are unnecessarily using more variables, unnecessarily loading the model. You are calculating more parameters, isn't it? More variables means more parameters. If you are unnecessary over parameterizing the model, then there is a penalty that it will call for, and from here you will come to know whether you have added a useful variable or not. If you do not use a useful variable, then for adjusted R square this rule is not applicable. The R square at the adjusted R square will straight away start dipping down. So what we do is we look at the difference between R square and adjusted R square, right? So we have to look at this difference. This is very important. So both are reported, right? So R square minus adjusted R square, and this value clearly should be less than or equal to 0.05, right? So now the question is, if it is not 0.05, it is more than 0.05, then what does it signify? It signifies two things. One, you have variables which are useless, which should be removed. So you should look at your data, you should remove variables. This is one. The second thing is, the second thing that people generally, if you go to the web and then people, and when you read what does the difference between R square and adjusted R square greater than 0.05 signify, then all of them generally will say multicollinearity. Multicollinearity is also the same thing. If there are two variables, what is multicollinearity? Multicollinearity means when the correlation between the variables is very high. Now, what does multicollinearity mean? Look at this. Let's say there are two variables, v1 and v2. They all sum up to the same thing. The basic principle is what I said, even if there is multicollinearity. Let's say there are two variables v1 and v2 and the correlation between them is 0.9. So what does this mean? That 90% of one variable is contained in the other, isn't it? The same pattern. So 90% of this variable is contained in this. So though we are using two variables, but 90% of the information is common, isn't it? So from an information theory perspective, though we are using two variables, but we are not bringing any new information, right? So that is why when the variables are correlated, then your adjusted R square generally would become high, right? The difference between R square and adjusted R square would be more than 0.05, right? So this is what multicollinearity is. Multicollinearity means that we, like example, you take one variable, right? That this is v1, and with a very small change you make another variable v2 out of it. Then what is going to happen? The correlation between, there is very small changes that you do, so the correlation between them can be 0.95, isn't it? So have you brought a new variable on the table? No, it's the same information you have repeated, isn't it? And plus you are not bringing any new information, plus you are asking a parameter to be estimated, isn't it? So that is what you come to know from adjusted R square. Either they are useless variables or there is repeated information, which you call as multicollinearity, right? Technically, we call it multicollinearity. Multicollinearity means the same information is repeated many times, right? So though we are in the impression that we are using n variables, but they are either n minus 1 or lesser variables. This is what it means. So this difference should not be more than 0.05. We have to look at that, right? This I've already told you. So the first block is the R square block. We look at the R square value. We feel happy if it is more than 0.60. This is one. And the second thing is that the adjusted R square will always will tell us that what is the quality of the variables that we have used, the quality of information that we have used, right? So it follows up something known as the principle of parsimony. So block number one. This is what we look at. Okay. Now let's come to the second block. So the second block is, so this is the model that we are fitting. If we look at this, then that's the model we are fitting. We are saying that this is our dependent variable y. This is the output of our model. We'll call it y hat, right? So this is the output of our model. What is that? Y hat is equal to beta naught. So this is the output. When I say hat, it means the output of our model, right? Beta naught plus beta 1 x1 plus beta 2 x, so on so forth till beta n xn, right? We are doing multi linear regression. So this is beta n xn, right? So this is the output of our model. And this is not going to be identically equal to our y, isn't it? It cannot be 100% reflection of our data, right? So that means the actual, this is my actual data, the actual dependent variable. This is my actual, and this is the output of my model, right? So there is going to be a variation in them, right? We know this is my model output, so this is my model output, right? So there is going to be some kind of a variation in them. It cannot be exactly a copy of it. So let's say this difference I call by epsilon, which is the difference, or I can call it the error. Error means not in the human term I told you. It is just like that my actual and the model output are not matching. So whatever the difference is, remember the scatter plot, we had drawn a line. The line was not passing through every point, isn't it? So it was missing. So that's what is the error part of it that we discussed. So this is the actual, this is the model output. So there is always a difference between them, isn't it? So what's a good model? A good model will always have this error as low as possible, right? So in the second block, we need to understand the faithfulness of the model. How well does it follow the data, right? So if it is following the data well, then this error would be low. And if it is not following sorry, the model is not following if the data well, then this there has to be some parameter by which we can understand that there is a difference there, right? So the second test is known as the F test, right? F test we discussed in the last session is used to understand the variance, right? So if I want to compare two variances, so if this is one data which has variance nu square, and there is another data which has a variance let's say nu2 square, right? You can denote, some people denote variance by nu1 nu2, some people may denote it by square, whatever, but these are variances. This is what I'm calling saying. So for a F test, always there has to be a null hypothesis that we discussed. So the null hypothesis is that nu1 square is equal to nu2 square, right? This is my null hypothesis. This is my null hypothesis, nu2 square, right? Or you can write it as nu1 square divided by, generally it is written in a ratio form. So nu2 square divided by nu1 square divided by nu2 square is equal to 1. You can write it like this, right? And this ratio of variances actually follow a F distribution, right? There is a F distribution because if you want to understand the difference of sample of means, then you were looking at a T distribution, right? We discussed a T distribution. The difference between a T distribution and a normal distribution is that a T distribution has bit fat tails, right? That's compared to a normal distribution. This nu distribution is a very skewed kind of a distribution, right? It is something like this. It has a very long this tail, and Now, if this is a distribution, then it should have parameters, isn't it? Every distribution has parameters. So what are the parameters of this distribution? The parameters of this distribution are degrees of freedom. So generally you'll see the degree of freedom of the numerator, degree of freedom of the denominator, right? So it doesn't have, if you want to calculate the mean and other mean, median and other parameters of this, then or the standard deviation, so then you have to calculate them. The actual original parameters of this distribution are generally mean of the numerator degrees of freedom, sorry, the degrees of freedom of the numerator and degrees of freedom of the denominator, right? So what we want to do is we do a F test. And what does this F test do? This sigma 1 square is, now let's look at this. What kind of F test we do? So we say the model explained by the variance. What is ultimately modeling is if this data represents 100% variations, right? Then how much of that variation is my model able to explain, divided by how much is unexplained, right? If the model is not able to explain, that goes into the unexplained part. You can look at it here. This is the portion explained by my model, and this is the portion which is unexplained, right? So it is new model divided by unexplained, or you may call it error, the epsilon, how much is gone into the, so I may call it an error, I may call it the unexplained portion, anything I can call it, right? So this is the hypothesis that it tests, that nu model divided by nu e. So ideally, if it is a good model, then what should happen? Nu model divided by nu e should be at least one, isn't it? So 50% of, so this I say that the 50% of my variance is explained by the model and 50% of it is unexplained, right? I'm completely, I don't know anything about it. This is bare minimum I need. Ideally this what I want is that this should be zero, isn't it? This should be zero, anything unexplained should be zero, and this should be the entire 100%, right? So if I divide 100% by zero, I'll get what? I'll get a very very large number, an infinite kind of a thing, right? So that means what I want is that my f value should be as large as possible, isn't it? That is what I want. So that is why I do a f test of this ratio, right? Nu model divided by nu e. So what I want here is that the f value should be at least 1, right? So that guarantees me at least a 50% of explained kind of situation, and 50% is still like unexplained, unknown to me, right? So I want f equal to 1. And also, as I said, because f, we need a statistical test to verify that this value is not by chance. At times values come by chance, right? So we want to eliminate the role of chance. So we want to say this value f equal to 1 is not by chance. So we want to look at the value of p. So the value of p should be less than or equal to 0.05, right? I'm including equal to because we don't want to throw away our model, right? And as I told you, equal to is my call. So it should be less than or equal to 0.05. So the second block is also known as the F block, F test block. What do I look at? I look at two things. One, the value of F should be 1 minimum, and the value of P should be less than 0.05. Now what happens if, let's say, the value of f is, let's say, 300? I feel very happy about it. Oh, the model is explaining 300 times of the unexplained, isn't it? That's a good idea. But if the value of p happens to be greater than 0.05, then that means this value is by chance. This will not hold. Next time if you have a similar data and you run the model again, you may actually not get this f value, right? So that is what it means. It means, have we received this value by chance, or is it like a value that really means something? Okay, so that's why we have to ascertain that both the things, f equal to greater than equal to 1, we want this, it has to be greater than equal to 1, sorry, it has to be greater than equal to 1, and p should be less than equal to zero point 0.5. These are the two situations we want. Okay, so here 50% of the variance goes into the unexplained part of it, right? That is what we want. A better situation would be if the variance explained is by the model is more than the variance which is unexplained, which is not known. So what we want is that the f value, the minimum value of f, should be equal to 1. Ideally it should be more than 1 always, and with that the p value should be less than 0.05. This is the second block, right? Now we go to the third block, the last block, and let's see what we do there, right? So this is the second block, the third block. The third block will consist of the beta coefficients, right? We said that the output of the model is ultimately y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta n xn. That is what the output of the third block is. So we look at the betas. So betas give us some value. So now what we do is we do a hypothesis testing around each beta. So the hypothesis is this, the H naught, the null hypothesis. The null hypothesis is this, H naught. That the beta in question, so I'm denoting it by beta I, right? Because we do it for all the betas. That the beta in question is actually equal to 0, right? Is actually equal to 0. This is what we want. And H1, which is the alternate, H1, which is the alternate, would be that this beta I is not equal to 0. So this beta I is not equal to 0. So this beta I is not equal to 0. Right? So what do we want? And we know the rule, right? And this all these testings happen at alpha equal to 5%. That we know, right? This, until and unless stated, your alpha is always going to be how much? It is going to be 0.05, right? So we want the null hypothesis to be rejected, isn't it? Otherwise, what, irrespective of what the value of beta that you are seeing there, it's actually a zero value, right? That is what it means. So what we want is that uh, this beta should actually be not equal to 0. We want the null hypothesis to be rejected and the alternate hypothesis not to be rejected. So we want is that the p-value should always be less than or equal to 0.05, right? This is what we want. If the p-value, what happens if in some case or in some betas, if you find a p-value which is more than 0.05, that means that particular coefficient should be 0 actually. 0 means that it is not playing any role in the analysis. That is what it results into, right? So once you have fit the model, always remember in modeling what happens is in the first iteration we have a model, right? Modeling is not completed modeling is not a one step kind of a procedure. We always need to be iterative. Iterations need to be done to fine tune. This is like tuning a radio. So we start with somewhere and then we turn on knobs and try to fine tune, right? So fine tuning is required. In regression, the process of fine tuning is known as diagnostics, right? So the first thing is we have a model, then we do a diagnostic. Diagnostics means we try to look at the quality of the fitment that we have done, and then we keep on fine tuning it till the time we get some result which is which seems to be okay. We'll never get something which is ideal. In typical business situations these days, we never get a model which is ideal. We'll never get r square equal to 1. That is not going to happen. But a satisfactory kind of a thing which is satisfactory, right? We say okay, seems to be satisfactory. So when you are doing, so this is what we look at the model fit, and we'll have to go iterative. So in the linear regression we have to do diagnostics, right? So diagnostics means that we have to check for certain conditions. So the things that we generally check for is about what about the error. So we uh, I mean we try to look at the errors, right? What kind of uh, how are the errors behaving? Let me give you a context. Like, why do we look at the behavior of the errors, right? So at time, think of chefs, right? Think of a chef, okay? And generally when they are, let's say, trained, when people join some course into hotel management, where some of them will become chefs, some of them will manage hotel, there are different kind of specializations there. So when people try to become chefs, the first thing that they are trained on is how to chop vegetables. Now think of a new chef who is going undergoing training in cutting cucumbers, right? So if a person is a good chef, that will what will happen is that irrespective of the size, and the cucumbers can be of varying size, isn't it? Some would be fat and short, some would be fat, long, all kinds of cucumbers we have. So think of a chef. If a chef is new, what will happen is his wastage, the top edge of the cucumber needs to be chopped off and thrown off. So if the size of the cucumber varies, generally what will the problem with the new chef would always be that his size of the wastage will always keep on varying. Now this wastage thing is something that we can probably equate with our errors, right? That's like our errors. So if the model is not good, our model is like the chef, and this cucumber size is like the data that we are getting. So if the data keeps on varying, what will happen? If the chef is not an expert chef, that means if the model is not a good model, then what it is going to do, it is going to throw different kind of errors. That is going to happen, isn't it? That's bound to happen. Okay, agreed. But an expert chef will actually do what? Generally, if you ask them, they'll say that the size of the wastage that should be thrown, that should almost be constant. That should vary between a very limited range only, right? So that's the concept of errors. The errors should not vary the way they want, right? They should be varied within some limits. So what we want is that the errors generated out of a model, they should always be normally distributed, right? They should be normally distributed. That's fine, right? So your error should be normally distributed. This is one. If it is a normal distribution, then it should have parameters. So the parameter should be that the mean should be 0. The error should be unbiased. It should have a mean 0. That means you should commit equal positive errors and equal negative errors, right? That's the logic. That's why the mean would be 0. If you have equal negative values and equal positive values, you are unbiased, right? Both the sides you are the same kind of values if we are generating, then the error is unbiased, isn't it? It needs to be an unbiased model. So that means the positive errors and the negative errors should exactly be equal. So if you find out the mean of such kind of errors, it would be 1, and the variance should be constant, right? I'm not saying 1 or anything, but it should be sigma. The variance should be constant. What does that mean? That if I look at 50% of the data, if so I can generate a variable, isn't it? So this is my actual y, and this is the y that I'm getting from the model, right? So I have these values, isn't it? This I have already fed into the system, this I can have from the system, and if I put it, I can get a third column, which is my error. So if I look at this column, then, and if I take half of the data, then also I should get the variance as sigma. And if I look at the full data, then also I should get a variance which is sigma, right? So this should remain constant. This is known as the situation of homoscedasticity, right? This is known as this. And if it is not, it will become heteroscedasticity. So this is known as homoscedasticity. A bit long spelling. Okay, so this is the condition of homoscedasticity, and condition of a constant variance, right? Uh, and if it is not, then it is a condition of this, right? A condition of heteroscedasticity, right? Uh, that we need to ascertain. So a good model uh, always does that. Okay, so we need to have this constant, right? So these conditions we need to check. So this is known as the diagnostics part, right? So the three blocks that we have done is for model fitment, and the rest of the things would be related to your diagnostics, right? So this is what we do. So regression, as I said, is one of the most used and abused kind of a thing because it is easy. So people were using it center, left, and right. Around 10 years back, this was the mainstay of everything. You ask people what to do, we'll fit a regression. Nowadays this regression has been replaced by clustering or classification. What to do, then people will suddenly say clustering, right? That always happens. Okay, so that's what is there. Now let's go to if there is anything left, yeah, we know this coefficient of determination, this and that, right? So now I think what we should do is we should try to why do you use multiple linear regression, any model for that thing? Because we are into predictive analytics, right? We are learning predictive analytics, so definitely we'll only learn those algorithms which can be used for prediction. So once you train the model, you can actually put it into operation and then it will keep on predicting values for you. This could be one reason that we want to use it for prediction. The second reason could be we want explanation, right? So there is a researcher who's just trying to understand, and he just thinks that probably this particular variable is is a dependent variable and all the other variables are independent variables. Then what will happen is that he can use this model and finally come to a conclusion that which variables are the actually the predictor variables, right? He may start from a large bunch of variables and he can use this model, reduce them and come to a smaller set of variables which actually are the predictors, right? And then theory building, at times you just don't know it, you can blindly like use this model, fine tune it, and then you get a theory that the housing prices actually depend on this, right? So you have a new theory. So from the data you can build theory. Many reasons. Explain it. Generally theory building you will not do because that is the job of researchers. So if you get into a research organization or something, or and theory building generally is more of an academic exercise. So till the time you get into academics, then only you will do theory building. So that's ruled out. More often it would be prediction. 90% of the cases it would be about prediction, and the other part is you might do explanations, right? That's the maximum that you can do. Okay, so okay, so now I think we are ready to run our model. Just remember that the sample size should be greater than equal to 50, right? That is what is required for running a linear regression. A good idea is that you should have 10 times the data as many independent variables you are using. And this applies when you are using ratio data. But if you are using categorical data, then what will happen is you'll require more data, right? So if you are using 5 variables, then if you have a 50 sample size, then till 5 independent variables it's okay. But if you use more than that, then the sample size has to increase, right? So some is, but generally regression is not a data intensive kind of a thing, right? That we remember. So that way it is easy, right? So this is what we are talking about diagrammatically. If you want to see the variations, if you look at it, this is what we are doing. This is the total variation. The outer circle is the total variations in Y. And what are we doing? This is, let's say, the variation which is captured. The red part, the core part, is the variation that is captured by the combination of independent variables. So because you are not capturing the entire thing, so the blue portion is which is the unpredictable thing, right? Something which is unpredictable, or you call it an error, whatever you want to call it, right? You can call it an error, right? So these are the conditions. Independence, as I said, that all the independent variables should actually be independent of each other, isn't it? So there should not be a collinearity or a multicollinearity. Normality, I told you, data should be normally distributed. Then the condition of homoscedasticity, which means that the errors should be, the variances should be like equally distributed. And then linearity, you only use a linear regression model, multilinear regression, only when you are sure that there is a linear combination, right? We know this, other things are not important. The output, I've already told you what kind of output you get, right? We'll discuss all this later on. So this is here, I've told you all. Now let us do one thing. Let us run this data and try to look at it. Okay, so I'll just open this and let's see if we have the code. So we'll run a regression model today and look at the output, right? That we should always do that. Okay, so this is the different data set that I'm running. I'm not using the data set which is uh, the housing data set. I'll request that all of you run it on that. So I'll take you through the entire thing from fitting the model to diagnosing it. So here we need this library. There is a library by the name of CAR. CAR stands for Companion for Regression. Okay, so this is needed. So I'm just getting the libraries. we get all the libraries. LM test is also one of the libraries. They are in library sandwich in library. So this sandwich or LM test, one of this library has a data set by the name of prestige, right? So if you look at this prestige data, this is about this data was collected in US. Actually, this is a US data set because India we still don't have this culture of collecting data. And if we collect data, we don't put it in the public domain, so it's not available. So this prestige data set is about what? Uh, our data was collected in 1974, I think, in 70s, early 70s, whatever it is, 74 or 72 at that point of a time. So this data was collected, and this was about the jobs and the prestige attached to that job was captured. That example, professors, they had a high prestige. US universities, I mean, if you look at professors, scientists, they have a high prestige. So a prestige score percentage was there. Then the designation, what kind of job it was, right? What is it, a manager's job, professor's job, that kind, right? Then we had the education. What was the education that was required for that kind of a job? What kind of earnings that were associated with that job, income, and what percentage of women were attached to that job? Why this data was done? Because gender equality studies have always been done, right, as a part of so many things. So the feeling was, or the idea was, that the prestigious jobs, that women are not employed in prestigious job, and this is early 70s, right, in US also. The feeling was that they are more employed in clerical kind of jobs, right, which doesn't carry too much of a prestige. So that was the idea. And We needed to test all that, and that is why this data is there, right? A simple data set so that you can understand. That's why we start with simple data sets. Okay. So okay, if you want to look at this, attach means I'm attaching this data set, right? So this is the data set we are attaching. So let's have a look at the data set itself, right? We always do a str. So let's do a str and have a look at this data set so that you get an idea of the data set also. So let's say this is P is capital here. So we are getting a prestige data set, and the data set name is also prestige, and a variable name is also prestige. So this is 102 observations, and it has 6 variables, you can see. So education is a number because it in years, average years of education that is required, right? Then income, right? I don't know what should be the unit of this. Is it in dollars or something straight away in dollars? So the number of women that are employed, percentage of women that are employed, 11.6, 4.02. This is the prestige score, right? So 68.8, 69.1, prestige score kind of a thing. This is census. So this is the census number. Which census number this is a part, right? So though it is shown as an integer, but it is more a time related kind of a job, right? Then there is a factor, right? So there are 3 levels, right? BC, professor, WC. I don't know what is that. We'll have to get into detail. Okay. So these are the 3 levels which are attached. So this is what the data set is about. And what we are doing, a simple thing, we are not taking all the data. You can see what we are trying to do is we are trying to understand that this prestige, this is my dependent variable. The data set name is also prestige. There is a capital P there, and in the dependent variable name is also prestige, but there is a small p there. Just look at this, right? So what we are trying to understand is that this prestige is actually defined by one, the education level, income, right? So if there is an income, and this prestige score comes out of this, and whether like more women are employed in it or less women are employed. If there are more women employed, probably it will not be a prestigious kind of a job, right? And the data that we are using is prestige. The command is very simple. You can look at it. This is lm. Lm is a part of the base package only. We don't need a special library for lm. So if you are thinking that the libraries that I've attached for executing this lm, no, that's not the case. These libraries I've attached just for diagnosis that we'll do later on. So the commands that in the diagnostic part that we do, they come from these packages, right? Example, I told you the condition of homoscedasticity. The base package cannot check it. So that is why I've used the car library there. But this LM is not a part of any package. It's a part of base package. If you don't attach any kind of a package, then also this LM can be executed. That's not a problem. You just need the data set and you can execute it. No package required, right? So let's look at the syntax because you are using it for the first time. So let's get introduced to it, and this is a kind of a universal kind of a thing. We'll keep on using it again and again. So LM, then we have the dependent variable, right? Then there is a tilde sign, right? This is the tilde sign which is on the left corner, right? So if you look at your in a other than probably a Mac laptop, you will generally look at it on the left corner. So below the escape button, you will find this tilde sign, right? And here you write the independent variables. Education, this plus plus plus, this is what you write. Now the question is good that we have only three variables here. Let's say if we have 300 variables, you can have a situation where you run a regression in 300 variables. So then the question is that will you have to type plus 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 300 times? No, that's not the case. What we'll do is if I prepare a data set, if I prepare a data set in which I knock off, let's say this, whatever variables I'm not using, example, this sensors and this type, if I knock it off, let's say I prepare one more data set, right? Let me do it here. So Prestige is another data set that I am preparing, and I'm naming it Prestige 1 is equal to, I'm using the earlier data set Prestige, and what am I doing? I'll use the square bracket. That means I'm subsetting it. I want all the rows, but I only want the 1, 2, 3, 4. That's the four columns. That's all. The four rows, right? So if I do it like this, right? And if I do str now, I can do str on prestige 1, prestige 1. If I do it like, let's see, yes, this is what I wanted. So I'll write this thing in a different way. I can write it like this then. So I'll take this, and how will I write the syntax in this case? I'll take this, and instead of a tilde sign, I'll remove this tilde sign. Okay, or not the tilde sign, I'll remove this plus plus everything here, and I'll put a dot here, right? I'll do it this way. So what does a dot mean? That other than the dependent variable, as soon as I put a dot there, it means that other than the dependent variable, everything is an independent variable. So at times when you don't want to get into this plus plus business, if you don't want to type, then you can just prepare your data set in such a way that it has dependent variable and independent variable. That's all, right? Nothing else. So if you do it that way, then you don't have to type anything on the independent side. You can just put a dot, and the dot means that everything else is a independent variable, right? So just remember that, and this tilde thing we'll use again and again. This is a universal thing. Now whatever modeling we'll do, we'll always use this, right? So it's good to get introduced to it, right? So, and very simple, it's a tilde sign. The here left hand side is the dependent variable. Left is always the dependent variable, and right is always the independent variable or variables, right? So it can be a dot or it can be plus plus depending on the situation. Okay, whatever it is. Okay. So let's
And Amit,
yeah,
just a minute.
yeah,
And if we just mention dot here,
yeah.
then it means it will count everything.
Then it will treat everything as an independent variable. If in this case, if you are asking if I remove all this, right? This is what you are saying. If I, yeah.
Yes.
So let's say I do it this way. Okay, let me assume for some time. I Let me put it here. Let's say I do it this way. I put a dot here, right? Let's say this is what you are saying.
Mm.
Now what will happen is
Mhm.
that it will treat census and type also as independent variable. That is the problem,
Yes.
right? So that I don't want. So that's why I'm not doing it. So what I'm
Mm.
doing here is I'm
So that's what I'm saying. If you don't want to remove anything,
hmm,
my all the uh, independent variables are continuous in
hmm,
nature,
hmm.
or then I can simply use dot.
Yeah, you can simply use dot. If I don't want to remove anything, then simply use a dot. That's all, right?
Yes.
Yeah, this is what it means. So this is your REG, and this is how. So let's execute the first model. Okay, so run. So you see that R is always silent. I mean, you see it has executed the command and gone to the next line, right? Nothing. It's not telling you anything, isn't it? So we need to ask, okay, you have run this, that's good, but show me the output. So how do we see the output? We'll have to write summary, as I told you. Summary. If I straight away write just this thing, let's say I write reg here, then what will it do? It will just tell me the call. Call is my formula and gives me the intercept, gives me the coefficient. This is my intercept, that is beta naught. This is, let's say, beta 1, this is beta 2, this is beta 3. That's all, right? It doesn't give me much information. But if I do summary, summary, all small, summary and reg, if I do it this way, then what happens is I get everything, right? So let's look at the blocks, right, that we are discussing. So where are those blocks that we are discussing? Now R is a free software, so definitely you will not see a very nice way of putting it up. But if you look at SAS or SPSS, all these things are put in a very nice manner. Probably the graphical thing is very nicely laid out there. But this is a free software, so it's like this, right? So this is your first block. This is your first. These two lines are your first block, right? So this contains this is just about the residual standard error. We may not understand anything out of it, but look at this line, like multiple r squared. This is your r square. How much is the value? 0.7982, or you can call it 79.82%. 80%. That's really very good. 80% is excellent. I mean, we have done a great job, right? That's one. But simultaneously, we need to look at adjusted r square. So what is that we discussed? That the difference between r square and adjusted r square should be less than or equal to 0.05, right? So here the difference is 0.006. That's good. That's less than 0.05. So no problem. I get a tick here. I say this is good. This part is good. I put a tick here. It has met my conditions. Tick, right? I'm happy r square is 80%. That will never happen in real life. Okay, so this is a small data set. That's why you're seeing such values. On larger data set, generally getting this kind of r square is almost impossible. Okay, so the second block I told you is the f block. So f block, what do you look at? Two things. F value. This is my f statistic. This is not statistics, right? A statistic means parameter. F parameter. Statistic, or we in machine learning we don't call it statistic. We generally call it the parameters. Okay, so this is your f parameter. The value is 129.2, right? 129.2. That is much higher than 1. We are happy about it, but at the same time we need to look, and these are the, this is the p value. So the p value is less than, you can see this value, very small value, isn't it? 10 raised to the power minus 16. 2.2 into 10 raised to the power minus 16, isn't it? It's very less as compared to what? As compared to your value of this, right? So it is much less than 2 0.05, right? So this also is a tick. We are happy about it. Now let's come to this block. So this intercept thing is just a balancing thing. It's a bias. We are not much bothered about it. So if it is, so this is the p value. I said this, the p is written as pr also. So let's look at this value. So this value, if you look at it, it's less than 0.05. Now, if you ask me a question, if had not been less than 0.05, then what? I mean, doesn't matter. This is something that's like a biasing constant. And what does the intercept mean? Why do we require an intercept? Intercept means that if all the input is zero, like example, if you look at sales versus advertisement. So let's say there is no advertisement. Will the sale become zero? No. So the relationship between, if you draw a relationship, if we assume that the sales depends on advertisement, this is a highly debatable thing in the marketing circles. But let's say this is correct. We belong to a school which says no, actually there is a relationship between sales and advertisement. So let's say sales is equal to beta naught plus beta 1 into advertisement. That's the equation. Simple linear regression. If the advertisement becomes zero, then will the sales become zero? No. Some sales will happen even without advertisement, right? Because of word of mouth, right? Because my company has employees, and the company employees and the relatives may buy. That's all. I'm not doing any advertisement. My neighbors will know that I I sell something like this, so they'll buy. So some level of sales will happen. That is that beta naught. So beta naught means if all the input is zero, the output cannot be zero. There is a base output that has to be there, right? So that's known as your intercept. Okay. So now so this is what the meaning of intercept is. Generally, we are not very bothered about it. Let's look at education. Okay. So education, the p-value is 2 into 10 to the power minus 16, so which is less than 0.05. So yes, this variable definitely is playing a role in defining the prestige score. Let's look at income. Income is also very less than 3 star. 3 star here, you can look at this, right? Z- so this is even correct at a level of 0%, right? 0.0% you will get 2 stars. 0.01 is 2 stars, and 0.05 is a dot out there, right? So so here this is a visual method of telling if there are any number of stars, that coefficient is useful, right? If we look at this, then the p-value is 0.06, right? So this is also okay, this is what we wanted. But look at this one, this is 0.770. So this variable is not playing any role here, this is not required. So what I'll have to do, I'll have to rerun my analysis. And how do I rerun my analysis? I'll have to remove women. In the second iteration, I'll have to remove women and run the entire equation again, right? This is the way you have to do it. And suppose you have 10 independent variables and there are three variables which come as non-useful, right? Or we call it non-significant, right? In there is a language we call it non-significant. Woman is non-significant here. Let's say there are 10 variables, you get three as non-significant. So what will you do? Remove all the three variables and then run it? Never, that should not be done. Bulk deletion of either variables or rows is not allowed. It has to be one at a time only. So whichever variable which will have this highest p-value, you will pick up that. That is the worst offender, right? So pick up that variable and rerun the equation again. Because you are removing a variable, so adjustment of betas will happen, generally will happen. And it might happen that a variable which was non-significant earlier, generally that will not happen, but we need to be cautious about it, right? So if a variable which was non-significant earlier might suddenly become significant now, right? That might happen. Okay. So don't remove variables in bulk, it has to be one at a time only. Please keep that in mind, right? That's very important. Okay, so this is what we have. So woman doesn't make any sense here. Now this is fine from a modeling perspective, this is fine that these two are ticked and the women are non-significant. But now the same thing, let's say, because you are explaining it to your sponsor, because research has a sponsor. In business, when you are working, then your business units are your sponsors, isn't it? So they give you a project, and at times they invest in resources also, right? So if you do a project, like typically in my company, when I'm given a project, the sponsors also gives me a budget that I'm giving you a budget, you can use it uh, for if required for some purpose. Okay. So your sponsor, who may be completely a non-machine learning person, he might ask you, what does this mean? Right? This is fine that this p-value has some problem, I understand. But from a business perspective, from an application perspective, what does this mean? What do I conclude out of it? So this here means that typically the prestige thing, the women was a non-existent entity, it doesn't explain anything, right? I mean, a prestige score doesn't depend on a women being there, or a high percentage of women being there, or a high percentage of women not being there. So the society was not, let's say, decreasing the prestige of a job if it has higher number of women. It's only that women were either opting or not opting for a job, that's a different thing. But the society definitely was not looking, the prestige score is definitely not dependent on more women being there or lesser women being there. So you can't conclude because there are more women in a particular job, that means it will carry a lower prestige. That's not correct, right? The prestige is dependent on income and education. And if a job is
Amit,
high,
your voice is break.
is breaking, it's okay now.
Yeah, in between.
Okay, so shall I repeat this thing again? Okay, so I'll
Mm-hmm.
repeat the thing again. Okay, so one is from a modeling perspective, this is fine. You may say that, okay, that this is not a useful variable. I'm knocking off. This is fine. But as I said, that your sponsors or the people who are going to be consumers of this modeling, they may be people who do not have a statistical background, right? Who absolutely they are not concerned with your p values, right? They have nothing to do with these p values. So if they ask what does this mean, then how do you explain it to them? So here in this case, when we say that the p value, that this p value of women is high and they are non-significant, that means that the prestige score is not dependent on the percentage of women working in it. That means what I'm trying to say is that the prestige score will not become low if there are more women working in that particular area. That job will not have a low prestige because there is a higher percentage of women working there, or vice versa. The prestige will also not become better if there are more women working there, right? That's what is not going to happen. It's not dependent on the women population, right? The prestige doesn't vary, doesn't depend on the percentage of women. Now, why probably there are more women working in some areas, and why there are more women working in lesser area, that may be the choice of women themselves. They feel that we should work here or that. But the prestige will purely depend on two variables, that is the education level. So more educated people will come, the higher would be the prestige. And if the income is more, the prestige would be more. That's common sense, isn't it? So if there is more income related to a position, definitely that's a more prestigious thing. So a president will have a very high salary, so that's why it's a prestigious thing. Of course, he'll be more educated also, and the prestige will not go away if that person happens to be a woman, right? So this is how we can explain it to our stakeholders. Okay, now we definitely know that there is the women definitely don't play a part here, that we know, right? So let's quickly look at one or two things here, right? So let's plot this prestige and income, right? Let me do a plot of prestige and income, right? So let's do this. Object prestige not found. Why I just now use this object prestige not found. Okay, let me do one thing. Probably it is confused with because of two. Whenever this happens, I'm attached. When I say attach, I told you this means that I'm saying this is my current data set that I'm using. And let me run it now. Yeah, it's earlier it was confused. Why? You know that we had attached two data set. There were two data sets, Prestige and Prestige 1. So as soon as I said Prestige, and both of these data sets has Prestige and income, right, as variable. So it was confused. It did not know where to go. Or I would have written here data equal to Prestige or Prestige 1. So I use alternate thing. I said attach. Attach means that now I'm only going to refer to this data set, right? So it immediately plotted. So so this is what. So now look at this. If I look at this, then this is not exhibiting exactly a linear relation. Very clearly, this is this kind of a relationship, curvilinear. So income and prestige, actually, if you look at them, they have a relationship. This is one, and this is like what? This is like a curvilinear kind of a thing. For a linear regression, we generally require this kind of thing, this or whatever, right? Or it may be this kind also, right? Drooping kind of a thing. Okay, but this is a non-linear thing. So one very important thing, we should always make a plot of, generally you can have your dependent variable here, you can have your dependent variable here, or whatever way, I mean it doesn't matter, and your independent variables here, right? And try to plot them, and plot them rather, it's very important in the diagnostic part. And look at them, are they sharing a linear kind of a relationship or a non-linear kind of a thing? If it is a non-linear relationship and you are trying to put a linear thing, generally your R square would not be good, right? Because this is a non-linear relationship, isn't it? It's not a linear relationship, and we are fitting a linear relationship out there, right? So when you do all these plots, scatter plots, you immediately come to know that there is an independent variable which actually is not linear. So what should be done? Let's say now look at this plot. What I've done is log 2. I've taken a log base 2, right? It's not a natural log. Natural log is always base e. E means 2.7178. That is the value of e exponential. This is a log base 2. So when I take a log base 2 and plot it, then let's see what happens. See, this is at least you can now say that it's more linear than what we had, right? So that means at times when your variables, when your dependent and the independent variable do not show a linear kind of a relationship, then to get the linear relation, what do? We have to do some kind of a transformation of the variables. So now what is happening is, instead of income, we are going to introduce log to income as the variable. Now this variable, if you look at it, is not, this doesn't have a power of 1, as I said, right? This has some other power. So when you do transformations have to be done. So this kind of a regression, generally you will start with a linear regression, and in many cases you will see that you will have to do a transformation. And when you do a transformation, then you lend into something known as a polynomial regression, right? This is known as a polynomial regression because your variables are not all raised to the power 1. You are believing that there is a linear relationship between the dependent variable, which is your prestige, and log 2 base of income. Okay, so now what have I done? I have done a transformation. So for transformation, I'll pass on I'll pass on two PDFs today, that those are known as box Cox transformations, right? So you might have to do Cox transformations, which are nothing but power transformations. That means they do a transformation something like this: a multiplied by whatever your variable is and raised to the power b. This kind of transformation, it's multiplied by some constant and raised to the power this thing, right? So box Cox transformation are power transformations and generally result into these kind of a things. Okay, so you might have to do some transformation. So now let's see whether my this understanding that whether when I transform this variable is the right thing that I'm doing, or is it the wrong thing. So let's go back to the regression again. Prestige is my dependent variable, education is here, right? I'm keeping women again, though I should but again, because I've done this transformation, so let me see if women starts making some sense. Okay, let me give it another chance. So I'll run it here, and then let me clear this space, and then you have this summary reg1, right? So let's look at what happened here. Let's start look at the r square. Now you can see the r square. Earlier it was 79.82, right? Now this is 83.51. That means I done the right thing, right? Adjusted r square, look at it, is 0.83. So this makes sense. The difference is definitely less than 0.05. The F statistics has also increased, right? So more explanation is being done by the model now. So the p-value, and this is significant. Education is significant, right? Log 2 base income is significant, and women is again not significant. Though the p-value has decreased, you can see this. It was 0.77 something. Now it has come down to 0.12, right? But again, this is not significant, right? It's not adding any value here, right? Now the idea of transformations is a very good idea. I've got a nice model fit, but let's go back again to the same situation. As I said, think about a stakeholder. Now a stakeholder comes again and he say, like, what does this business mean, right?
Amit,
Hmm. Yeah. Yes, Ajay. Okay, I lost my audio connection
Yes, you lost in between.
in between. Now it is okay.
That is okay. So, Amit,
Hmm.
I have one question here.
Yeah, yeah.
So, from the p-value, we can identify whether one of my variables in independent variables
Hmm.
is significant or not.
Yes.
Now if I have multiple variables,
Hmm.
maybe 10, 15, or 20,
Right.
I cannot check scatter plot for every variable. It could be a cumbersome thing.
Yeah, it can be
So
cumbersome.
how do I get an idea which of my variables need to be transformed? Looking
Okay.
into this
Okay.
summary.
Okay. One. No, no. Looking at this summary, you cannot find out anything. Right. This is point number one.
Okay.
This absolutely, if
Mhm.
you look at this summary, and if somebody tells you that I looked at the summary and I found out that what the transformation was, no, that's not
Mhm.
possible at all. In R, that's why I said that these coding languages are good. What I can do is I can just say I can run the Cox transformation for all my variables, right? So I can write a very small program in the beginning itself. So what I'll do
But
is,
how? But the thing is,
hmm,
oh, when do I get an idea that I need to
yeah, yeah,
transform?
that's what I'm saying. That's what I'm saying. Now, let's start with this situation, right? Let's start with this situation, right? So what I'll do is that I need to transform, I need not need to transform, is one method is I draw those kind of graphs, right, scatter plots, and then try to look at them. But that's a visual method, isn't it? I drew a line, and this was very, let's say, visual. I mean, I'd seen, so I drew a line which was looking like a linear kind of a thing, and I assumed that there would be some kind of a thing, so I did some kind of a transformation. This is one way. The other way, that practically what people do is that before they start it, you can just put, so what does the box Cox transform mean? It tells you that prestige and education, what kind of a relationship makes sense, right? So everything will come like a into variable raised to the power something, right? Now in the box Cox thing, all those values would be calculated, right? This is one. The second thing I'll write, wherever like this a and this power are significant, the power is significant. Let's say if the power is more than or less than zero point 0.5, generally like anything which is till more than zero point 0.5, like let's say zero point 0.6 or 1, we generally don't, we try to avoid transformation. We know there would be a little bit of distortion there, that's okay, but I try to avoid that transformation, right? But if the values really, you can put a cutoff of zero point 0.6 or minus zero point 0.6 for that matter, right? Anything which is less than zero point 0.6, negative, of course, is a serious thing. Then identify that variable. There, I need to have a transformation, right? Now, you may say that that is a power transform, and here
Could you please repeat
I'll just
last
repeat.
couple of lines?
Right. So let me open a slide for you, right? Let me open a new slide. So what I'll do here is, let's say these are my variables, v1, so on and so forth. These are large number of variables. This is what you are saying, right? We have n number of variables here. So what I'll do is I'll take all of them variable, make a small function. As I said, I can write functions. I told you, I don't know how many of you visited that site. So I'll write a small function. What will this function do? This function will run a Cox transformation, right? This function will run a Cox transformation on all the variables, right? Because I'm doing it in an automated mode. If you have a large number of variables, automation is the way to go, right? It's always automated. You cannot individually look at things. So let's say this is a Cox transformation I'll do. So what will the Cox transformation do? It will give me a listing like this: v1, v2, and so on and so forth here till vn, right? And it will give me the power that is required, the power transformation that is required. Believe me, it will give up, it will never give a power of zero. Power of zero means that there is no transformation which is required. Use the variable as it is, right? Don't do anything. Or sorry, the power of one. So it will never give me a value of one generally. So it will give me all sorts of values, right? Example, it will give me 1.2 here. Here it may give me -5. Let's say this is extreme value, it will never come. -5. Let's say here it gives me a value of 0.3, right? And somewhere it gives me a value of zero point 0.7 or something, right? It will give me these kind of values, right? So and these are again, n values are like large values. So what I'll do is I'll write another function on it, very simple. I'll write, this is my function one, and I'll write another function here where I'll say, so this is my function 2, let's say. And what I'll do in this function 2 is that I'll say wherever I'll define values in this power thing, wherever the values generally will lie between zero point 0.6 and let's say this range, generally 1.2. Don't do anything with that. Use that variable as it is, right? These rules I can write, there is no problem. This function will contain two rules where it says if this power thing, if it lies between zero point 0.6 and 1.2, you let the variable as it is, right? Don't do anything to the variable, right? And if the power is anything other than this, right, then do a power transformation, then power transform, right? Automatically the data would be ready for me, right? Do a power transform. So that is the beauty when you are working with a coding kind of a language, you can do whatever you want. So I'll get a power transform. So that means a power transform generally approximate all kinds of a function. So that means a square root can be approximated by a power transformation, right? So there is a power transform for this, right? For a log, normal log also there is a power transform. All of these functions can be approximated by a power transformation. That is why Cox power transformations are popular. Let's say this is another kinds of power transform which I represent by P2, this can be represented by P1, right? So a wide array of functions that we know, example square root or squaring of x. If you want to square x, of course this power will come actually as 2, right? If you don't want to use x square, so you'll get a power of 2 here directly, right? But believe me, generally what happens is also, when I'm saying this, always keep in mind, if your power, generally what happens is if you use powers of 3, right, if you use powers of 3, any function can be beaten and fitted into a good R square. Try this on Excel. You can open an Excel sheet and you can fit a straight line there, and that straight line you have that option of looking at R square and looking at transformations, isn't it? So if you try to use a polynomial or x3, if you transform your independent variables to the power of 3, they'll always start giving you a very nice R square value. That means anything which is transformed to the power 3 or more will always give you a R square which would look very good. But the utility is reduces to almost nil, right? So your, what I'm trying to tell you is that if your power transformations comes to 3, that means in all practicalities don't use that variable. Probably it's not useful. You cannot explain it to the business also, right? It's not useful from a business perspective also. From a modeling perspective, that may be a very good exercise. From academic perspective, that's a very good exercise. But from a business perspective, it's useless. When you go and talk to your let's say stakeholder and tell him that this variable will work when you raise it to the power 3. Let's say you get an equation which says advertisement equal to beta naught plus beta 1 into x raised to the power 3. So advertisement raised to the power 3 is the best fit. Now what does that mean? How do I operationalize all that? God knows, right? So that is the problem. So I'll always say regression, that's why, is a tricky thing. From an academic perspective, you can fit R squares and all these things. But when you actually want to use it in a business perspective, there is very little space to maneuver. You cannot use any kind of transformation that you want. So if it is telling you the women thing can also be fit, if I put a Cox transform to it, it will suggest me some transform where the women will also become will become significant. That is going to happen, but I'm not going to do it, right? So what I'll do is, if the power transformation requirement is too high, that's why I said zero point 0.6 to 1.2, I'll not even bother about doing any transformation. I'll take the risk and go ahead. And if this transformation is lies somewhere between, let's say, minus 1.5 kind of a thing to probably zero point 0.6, I am ready to do that transformation, because or let's say maximum till what, -2 here, and from let's say 1.3 to 2. If this kind of transformations are being suggested, I'll try to use it. Otherwise, I will not, because that will become, from academic perspective, that's a correct thing that I'm doing, but business utility is almost zero out there, right? That we need to keep in mind. Okay, so we have to look at that aspect also. What are we doing? Okay, so this is how you take the decisions, and your thing is right, that you cannot visually look at things when we are talking about these transforms. That's impossible. 10 12 things, okay, we can understand, that's fine, right? That's not a problem, we can understand that. Okay, this is how we deal with that. So this makes sense here. This is what we are seeing, right? So okay, now if you ask me what log 2 base income means, this is a logarithm based to income. Now if your stakeholder asks what does that log 2 base income mean, to a level you can explain, but after some time you can't explain it, right? But so this is one aspect. The other aspect is your stakeholder is not interested in understanding the model, right? At times he's not interested in the model. What he wants is a prediction. He wants that you fit all this into a production kind of a thing, and this should predict the right value. If he's interested in only understanding the output value or the prediction part of it, then you can make your model as complicated as you want, because you don't have to explain them. The business doesn't have to use these levers. So whenever the business is not using these levers, is not acting upon them, and you are just using it for a predictive purpose, you can use any complicated thing. That's why if you look at classification models which are very very complicated, nobody can explain them. They are just used for prediction purpose. Nobody tries to understand what is the equation, is the value transformed, not transformed. Nobody has anything to do with that. This, and that's why people say that the machine learning thing is like a black box. That's the reason, because people don't understand what's really going inside it. But it is giving some value which is useful. It's making some predictions which is useful, isn't it? So you have to look at the situation and then work, right? That's what I'm saying. So anything is possible. You can automate all this. That's what I'm saying. Okay, if there are large number of variables, whenever there are large number of variables, programming languages give you this flexibility. You can write small functions and automate this entire thing. Okay, so that's what is. Now once we have understood that women probably are not making sense and log 2 is making more sense, so let's run this. This is the last model that we are running, and this is what we do. And let's look at summary. So what changes? Nothing much. If you compare it with reg2 here, I think nothing much changes there. So reg1, so 83.1 here, it has gone down. Let me show you a summary of the last reg1 also, so that you can compare. You can look at the r square thing. I told you it is going to decrease only always, right? So look at this r square. This was 83.51. Now what is it in? And if you look at this, this is 831. It has reduced because you have removed a variable, women. Look at adjusted R square. It was 0.8275. And what is the adjusted R square here? 0.83. It has improved. That's what I was telling you. Look at adjusted R square. It has improved. So adjusted R square tells me that I've done the right thing. I've removed a variable which was useless. But the R square is guiding me in the opposite direction, isn't it? It's telling me that probably you have made some kind of a mistake or something. Okay, and in this, if you look at this, then because there is no women, so all of them are useful, right? So that's why I told you that r square can be misguiding. This is what I was telling you. It has dropped, isn't it? The drop is very small, you may say, but there is a drop. That's what I'm saying. Here it is 0.83, and there you'll see up here also we see a smaller drop probably, but the drop would be generally be lesser, and these two will start coming close. As soon as your model starts making more sense, the difference between r square and adjusted r square will start decreasing, right? That will happen, and that gives you an idea that yes, you are doing the right thing. Okay, so this is known as the model fitting part of it.